1, 2. Right, I want to explain the twin paradox using the time dimension explanation, which is just light signals sent from one to the other. So I'm going to need this. So I'm going to have to split the screen and get something up. This one. Yep. So I can draw on this one. So you can see that different velocities, different things happen, things change, but at 0.6, a velocity of 0.6 exactly, it looks like this. So what happens is, here's Bob, flies out along the gamma line to Alpha Centauri, which is here according to him, and then he flies back to Alice on Earth. So this is Alice's space line, and this is his space line is gamma plus gamma, whereas hers is just 1 plus 1. Okay, so Bob is flying away from Alice in the time direction, and then all of a sudden he's flying towards us, back towards her, because it's not a realistic situation. There's no acceleration. He's just flying at 0.6 c away from her, and the next second he's flying at 0.6 c towards her. But what would happen to the light waves that she sends him? Well, first of all, as he's flying away, they're going to be redshifted, and the redshift will be this distance, which is 1 over t, plus this distance, which is 1 over l. So if you add those two together, then you're adding 0.75 plus 1.25, so it's going to be a redshift of 2. So the redshifted wavelength is going to be 2, but because Bob changes direction, he is going to immediately start feeling blue shifted waves. So it's like he's changed direction in the ocean, for example, and the waves he's going with the waves, and then all of a sudden he's going back against the waves. So at halfway point, he's all of a sudden getting blue shifted waves, which is it's actually gamma minus 1 over t, so it's 1.25 minus 1.75, which is a proper velocity, by the way, because it's Alice's distance over Bob's time, and that's actually 0.5. So the wavelength, the blue shifted wavelength is 0.5, and this, we're talking about the parallel direction here, because the perpendicular direction would be a blue shift of L and a red shift of 1.25, which is gamma. But because they're flying away from each other and then towards each other, it's a parallel red shift and blue shift. So what is the equation? Well, go back to here, come down to here's the redshift. As I said, it's 2 at the moment, and the blue shift is 0.5, and if you multiply them together you always get 1 regardless of the velocity. So therefore I'm going to have to go back to a full screen. Now the full screen, here we are. looking at redshift, blue shift, and this is the calculation for Bob's. For what Bob determines is Alice's time. So he takes his time, which is t, multiplies it by gamma, it turns out, and comes up with Alice's time. So for half the time he's getting redshift, and for half the time he's getting blue shift. And because of this fact here, if I'm interested in the frequency, not the wavelength, so I simply change the sign from plus to negative, and then I get the frequency instead of the wavelength. So that's why the signs are back to front. And in Alice's case, it's a little different, because for 80% of the time she is receiving redshifted waves, and for only 20% of the time she's receiving blue shifted waves. So therefore, if you multiply that, you find that relative to her time, which is t over L, Bob's time is 0.8 of that. So t over L times L is actually just t, which is Bob's time. So they calculate each other's time to be different. I better explain the 80% and the 20%. So over here you got Alice. As I was saying, Bob experiences redshift for half the time, whereas Alice experiences redshift for 80% of the time, and which is exactly that amount of the time. And she experiences blue shift for that amount of the time, which is precisely 20% of the time, whereas Bob experiences blue shift for 50% of the time. So that's the time reason for the difference. That'll do.